Welcome to Future Dr. H Numerics. Today we are going to focus on EMF graphs. We are also going to focus on the theory, and then we do equations. So this video is the first of a series where we are going to do different EMF graphs. So this is the paper that we are going to focus on. So it's just a group of question papers that we'll be dealing with. So as you can see, the first graph that we are going to deal with is like this. So let me just draw it so that we can do the theory based on this. So I'm not gonna do a lot when it comes to drawing it. I'm just gonna put it like this, and then I just put this, and then this side is V external, and then when you go down we find a current, as you can see there. So I'm showing you how the graph appears in an exam, and then how to interpret that graph if it appears in an exam. So it's usually drawn and appears like this. I hope I don't ruin my other lines. So like this. So that's our graph. So it's a potential difference versus current graph. So let's see how we are going to derive this graph. So let's look at the graph here. So looking at this graph, the first thing that you have to know is that this is a straight line graph. As you have to know, this is a straight line graph. So every straight line graph falls under the equation y equals to mx plus c. That's where each and every straight line graph falls. So another thing that you have to know about this graph is that all these EMF graphs are derived from the EMF equation, which is E equals to I R plus R. Those are the equation in which all these graphs are derived. So now we have to reconcile. We have to reconcile this graph with this graph. So what do we know here? We know that current, or our I here, is the X variable, is equals to the current. What do we know from this graph? We know that our V external, or our V, is our what? Is our Y axis. So we have to reconcile an equation in the form of Y equals to mx plus c. So we are going through this content, and then after we are going to apply this theory to the what? To the questions. So now let's reconcile. What is needed here? We still need this. This is needed in the equation because it's what is our X variable, and also we also need a V external. We don't have a V external, but we know that a V external is made of what? V external equals to I plus R external. So that's how our V external, we find it. So now when we come to here, we just let this and say IR plus I. So we just like multiplied. We just multiplied and removed the brackets. So what do we know that this is equals to? This, as we did here, this is equals to the what? This is equals to the V external. So this is equals to the V external. That's why we are allowed to come here and say V external, which is our Y. So this is our V external plus what? Plus IR. And then we come here, our EMF. So we need our equation in the form of Y equals to mx plus c. And then it means that we are going to rearrange the equation. We're rearranging the equation, and then we are going to kick this one that side. So it's going to be EMF minus IR. So now this is our X now. This is our X. So we want our X to be directly at this position now. This is on our Y. We have done well with our V. And then now we are going to say negative R. This is in the position of X now. It's still our current there, plus EMF. So as you can see now, this is Y equals to mx plus c. So we must see the corresponding items. So the corresponding items, this is our this is this, and then this is this is this. So what does this tell us? It's very much important. We were not just manipulating this equation to make it seem like it is more complicated for nothing. So this tells us that now this C is always our y-intercept. So every time in graphs like this, if you see your y-intercept, the y-intercept will give you what? The EMF equals to E, as you can see. So this point, if you see a graph on a question paper, like that question paper that we saw at the beginning where I saw this graph, it will just appear like this, and then they will say, what is the EMF of the battery? If you are not able to manipulate the equations like this, you won't be able to know that, oh, if here it's 8 volts, so you'll just take the value here where the graph cuts the y-intercept, because the y-intercept is always equals to the EMF in this graph. So if they say, look, find the gradient, they won't say find the gradient, but they will say find the internal resistance of the battery. And then you will be looking to say that you are not given a circuit, you are not given you are not given any resistance, but they say you must find the internal resistance of the battery. What do you come and do? You come and calculate the very same way you calculate the gradient, and say gradient equals to what? Equals to negative R, and then you see what? Gradient equals to negative, and then change in y over what? Change in y over change in x. So that's how you find it. So you just come and find your gradient, and then that gradient you multiply it by negative. You'll find your gradient. So what else do we need to know about this graph? So let me just rub here, and then after I rub, I'm going to teach us how to. After I rub, I'm going to teach us how to interpret and understand this graph. So I'm just going to rub here, and then I put what we have found here. We have found that the gradient always in this graph, the gradient equals to what? Negative R. And then what else did we find? We find that the C, or the y-intercept, equals to the EMF. This is the gradient. This is the what? This is also the y-intercept. And then what else? We have also so that here, but it's on the graph that current is equivalent to the X, and then voltage is equivalent to the what? The voltage is equivalent to the Y. So this is what we see here on this graph. So, and then now let me wrap this side so that we can deal with that questions. So I hope, before we go to the question, let's finish one more thing about the content. Let's finish one more thing about the theory before we go to the. So on the gradient, it's simple. We just in this formula of the gradient, that I said equals to change in y. Gradient equals to change in y over change in x. You just come and take any 2 points. Any 2 points along this line. You just this point will have an x variable and the y variable, and then you come and substitute. So that's it with the gradient. Now, how do we understand this graph? Because this graph might be a little difficult to understand, because how is it that when the current increases, the V external decreases? Current increases, V external decreases. So you have to understand it using again this formula. You have to understand it using again this formula where we had said our equation equals to y equals to negative R multiplied by I plus EMF. So now let's understand this equation. So this is not this is y or what, or V external. So let's understand this equation. So now in this equation we're just going to write it in a nice way, and then we say EMF minus what? Minus IR. We just shifted this. So let's understand this. So now, how is it that when current increases, the V external decreases? So let's check. When you check on the total current of a cell, if the total current increase, EMF is constant. EMF is constant. Total current will increase. Therefore, a greater value will be subtracted from the EMF. Therefore, V external will increase. They are like inverse of one another. So let's see the opposite. When we check the opposite, if current decrease, a lesser value will be subtracted from the EMF, which is constant. Therefore, this one will increase. It's just like the difference between V lost and V external. So let me explain. So the EMF is made of V lost or V internal plus what? V external. So now this represents what? Let me just shift them around in the way that, but it is not necessary. So this is like our IR. This is our V lost. So let's take it like this. When current increases, if current increases like this, the V lost are going to what? Are going to decrease. Therefore, V external increases. So if a current decreases, the V lost is going to decrease. Therefore, V external will increase. Because what? Because they are sharing the same EMF. Because what is the V lost? V lost is the energy or voltage of a battery used to overcome internal resistance. So there is some voltage which is taken inside the cell before it goes out to the V external. So if less energy is taken before it goes outside, it means that there will be more energy for the external circuit. If more energy is taken, if we check that here, more energy is taken in what? In the battery, in internal resistance. This is the V loss of V internal. Therefore, there will be less energy going outside. So that's how you understand this graph. That's why they are inversely proportional. So the last part of this video, we are just going to focus on the question. So let me find the question, and then this is the question. So I need to expand it. I can see it properly. I'm not sure if you can see it properly there, but let me just find a way to see it properly. Yeah, I made a little so okay, there it is. I'll just read the question now. I made a full screen. So now in this question, we're just going to apply our knowledge now. Let's see if you were able to learn anything now. So now let's go to the question. It says that I think let me just make this bigger. Let me just make this bigger. If I make it bigger, it will cover this. So let me just read it here. The EMF of internal resistance of a certain battery were determined experimentally. Instead of state Ohm's law in words. Ohm's law states that the potential difference across the conductor is directly proportional to the current passing through that conductor, provided the temperature remains constant. So it's just this. It's just this equation of say V equals to IR when we see that the current increases, the potential difference also increases, and vice versa. So now it says that the data obtained are used in this experiment, and then we see the graph see that draw the line of best fit. So we are just drawing the line of best fit across those points. Let's take it that this is the line, and then now it says that write down the value of the EMF. So it says that write down the value of the EMF, and in the graph there we got that our EMF equals to what? Our y-intercept. Our EMF equals to our y-intercept. We just come and take our y-intercept from the graph up here, and then so if you check here, we're just going to come and take our y-intercept here. As you can see that this here is the y-intercept here. I'm not sure if my mouse is visible. This is our y-intercept now. So we are just going to come at our y-intercept and take that value to say that our EMF equals to 5 volts. No calculation. So if you do not know how to manipulate in exam, you have to do that process that I came with. It's either you use it's either you come in the exam room having cramped this equation, or you say that you come in the exam room knowing that you have to derive and then find your y as this and find your mx plus c. It's either you derive or you cram. But there are more graphs. There are like 4 graphs that we are going to do. Some of them will do them when you go further. So cramming, you might end up mixing things. So it's better that you just understand that you have to derive when you are in the exam room, and then if you derive, you do this. You come and do this. So when we continue with the question, it says that determine the internal resistance of the battery. You see, there is no value given here. There is no value. You are not even given the value of any step of resistance. You just have to use the graphs. Some question even say that without using the known equations. That's what it says. So now we just come and say that internal resistance equals to M. It needs you to derive and use this, that internal resistance is equals to the gradient. So you just come and say M equals to negative R, and then you just come and substitute there. When you come and substitute, you say negative. So it's either you just say this negative change in what? Change in Y over change in X. And then you just come and take any 2 points on the graph. You take any 2 points, you substitute. So it's better that you pause the video and then you do and then you come and see the answers. And then you go and see points which you can use there. Let's also try to zoom there on the graph. Let's try to zoom. So when we try to zoom there on the graph, we'll see that which points can we find, which points are visible there. So that's need me to look more closely. So you just come and take, let's count. So we are counting with what? 1, 2, 3, 4, 5, 6, 0,1. We are counting it at the Y. We are counting with 0,1. So now let's take the first point and the last point. The first point and the last point. So this is gonna be let's count together. So this is gonna be here as 1, 2, 3, 4, 5, 6. So it's gonna be 4,6. 4,6. That's our what? Our Y. So now the 2 points that we are going to use. So this first one is what? The Y is what? 4,6 volts. So let's get the current there at 4,6. So down here we are counting with what? We are also counting with 0.1. So because we are counting with 0.1, let's count from this side. I think this side is closer. 1, 2, 3, 4. Okay, you can just count here. 1, 2, 3, 4. So it's 4. So it means 2 minus 1 minus 0,4 is 0,6. So 0,6. So that's our point here. So now let's get another point. So, but you can even use this. You can even, it's like a straight line. You can use 1 point, but for more accuracy, you can use 2 points. So now, when it comes to your Y, you come and use this. There's 1 here on your Y, and then so is it 1 on the Y? Yes, it's 1 on the Y there. And then you